we often accept the boundary between the familiar and the complex. We see the concrete world, a rock, a planet, a star. Then we are told it's all made of particles, tiny, distinct points of matter and energy. But is that the bottom floor? What defines these fundamental pieces? Science rarely settles for the first answer. It keeps asking why things are the way they are, pushing past the seemingly solid surfaces of reality. It searches for a simpler, more unified explanation underneath the apparent chaos. What if the properties we observe, from the smallest quark to the largest galaxy, are just different expressions of one underlying entity? If you enjoy peeling back these layers of reality, a quick like and subscribe helps others find these conversations. Stay with us as we look deeper than the particle. The concept of string theory did not begin as a deliberate attempt to explain the entire universe. It emerged, in many ways, unintentionally during the late 1960 seconds. At that time, physicists were facing a significant challenge. They were trying to find a single, unified, mathematical framework that could describe all the fundamental forces of nature. They had very successful theories for electromagnetism, which governs light and electricity, and for the nuclear forces that hold the centers of atoms together. But the force of gravity, as described by Albert Einstein, simply would not fit into the same picture. It remained separate, a puzzle that resisted unification. While working on mathematical models for the strong nuclear force, some researchers stumbled upon a peculiar formula. This formula, originally intended for something else, seemed to describe the interactions of particles in a new way. Instead of treating particles as single, zero-dimensional points, the math behaved as if these particles were actually tiny, one-dimensional loops or strings. These are not strings in the common sense, like a shoelace or a guitar string. They are proposed to be the absolute smallest, most fundamental building blocks of reality, existing at a scale trillions of times smaller than a single atomic nucleus. They are so small, they can never be seen directly. The central idea of the theory is what these strings do. They vibrate. The theory proposes that these strings are the only true, fundamental objects in the universe. Everything else we see is just a consequence of their vibration. In the older, standard model of physics, the universe is filled with a large variety of different particles, electrons, quarks, neutrinos, and photons, among others. Each is considered a separate, fundamental entity with its own unique properties, like mass and charge. String theory offers a much more elegant, simpler picture. It suggests there is only one ingredient: the string. A string that vibrates in one specific pattern, or note, will appear to us as an electron. It will have the exact mass and charge of an electron. If that same string changes its vibration and moves in a different pattern, it might appear as a photon, the particle of light. Another distinct vibration pattern would produce a quark. Crucially, the theory predicted that one specific vibrational pattern would have the exact properties of the graviton, a theoretical particle that physicists believe must carry the force of gravity, but which has never been found. In this way, string theory doesn't just describe matter, it unifies matter and forces. All the complexity we see is just different music, played by the same underlying string. It is important to clarify what vibration means in this context. It is not a sound. Sound, as we experience it, is a mechanical wave that needs a medium, like air or water, to travel through. These fundamental strings are not vibrating inside of space. Their vibrations are oscillations of energy itself. They are patterns in the most basic fabric of existence, and these patterns are what define the properties of particles and, according to the theory, the fabric of space itself. The main reason this idea captured the attention of so many physicists was not just its elegance, it was its potential to solve the single greatest conflict in all of modern science, the incompatibility of our two most successful theories. Physics currently rests on two main pillars. The first pillar is general relativity, Einstein's theory of gravity. It describes the universe on the largest scales. It explains how planets, stars, and galaxies move by stating that massive objects curve the fabric of space and time. This theory works perfectly for describing the cosmos. The second pillar is quantum mechanics. This is the rule book for the universe at the smallest scales, the world of atoms, electrons, and subatomic particles. It is a strange world of probabilities and uncertainty, but its mathematics is also perfectly accurate. It is the foundation for all modern electronics, lasers, and computing. Here is the problem. These two pillars do not work together. General relativity is a smooth, classical theory, while quantum mechanics is chaotic and built on probabilities. Physicists need to combine them to describe extreme situations, such as the exact center of a black hole, where immense gravity is crushed into a tiny quantum-sized space. They also need to combine them to describe the very first moment of the Big Bang. But when they try to put the equations together, the math breaks down. It returns answers of infinity, which is a mathematical way of saying the theory is wrong and has stopped making sense. String theory offers a pathway out of this conflict. The mathematical problems in combining the two theories arose because they were based on particles as infinitely small points. By replacing these zero-dimensional points with one-dimensional strings, the math changes. These strings have a tiny, but not zero, length. They smear out the interactions, preventing the math from breaking down at zero distance. Suddenly, the infinities that plagued the calculations disappear. In this new framework, gravity, as described by general relativity and the rules of quantum mechanics, can finally coexist. However, this mathematical solution comes with a major requirement, one that is very difficult to accept. For the equations of string theory to be consistent, the universe cannot have only the dimensions we know. We are familiar with 3 dimensions of space, length, width, and height, and 1 dimension of time. String theory requires the existence of extra spatial dimensions. Different versions of the theory demand a total of 10 or even 11 dimensions, meaning 6 or 7 extra spatial dimensions. If these dimensions are real, why can we not see them or move through them? The theory suggests that these extra dimensions are compactified or curled up at an unimaginably small scale. We can use an analogy. Imagine a garden hose stretching across a yard. From a great distance, the hose looks like a one-dimensional line. You can only move back and forth along its length. But if you get very close, you see it has a second dimension, the small circle you can move around. The extra dimensions of string theory are thought to be like that tiny circle, but curled up trillions of times smaller, existing at every single point in the space we see. They are so small that we, and even light, cannot access them, leaving us with the illusion of a 3-dimensional world. It must be stated very clearly that, for for all its mathematical beauty, string theory is entirely unproven. It remains a theoretical framework. No experiment has ever produced direct evidence for strings or for extra dimensions. To test the theory directly, to actually see a string, would require energies far beyond any particle accelerator humanity could dream of building. The Large Hadron Collider, our most powerful machine, is not nearly powerful enough. This lack of testability creates a deep debate within the scientific community. Some critics argue that because the theory cannot make unique predictions that we can test in an experiment, it is not truly science. They worry it has become a form of philosophy or abstract mathematics, detached from physical reality. On the other hand, its supporters argue that many great scientific ideas like the existence of atoms were untestable for decades or even centuries after they were first proposed. They believe the mathematical consistency and the fact that it solves the conflict between gravity and quantum mechanics are too compelling to be a mere coincidence. They continue to search for indirect clues, perhaps in the patterns of cosmic background radiation or in the behavior of particles that might hint the theory is correct. This brings us back to the central theme of vibration. We are constantly surrounded by vibrations. We understand sound waves traveling through the air, light waves as oscillations of electromagnetic fields. If string theory is an accurate description of reality, it suggests that this principle of vibration is the most fundamental rule of all. It proposes that the universe is not made of static, solid stuff. Instead, at its very foundation, reality is a process of vibrating energy. The properties of everything we see are just the frequencies and patterns of these vibrations, unifying all matter and all forces into a single underlying concept. For many centuries, our understanding of the physical world was built upon a very straightforward idea. We believe that if you take any piece of matter and break it apart into smaller and smaller pieces, you will eventually reach a final, fundamental component that cannot be broken down any further. We came to call these the fundamental particles. This way of thinking gave rise to the Standard Model of Physics, a framework that describes the universe as a collection of basic building blocks: electrons, quarks, photons, and a few others. This model has been astonishingly successful. It is the foundation for our understanding of chemistry. It allowed for the invention of all modern electronics, from transistors to lasers, and it lets us predict the behavior of matter with incredible precision. But this model, for all its power, leaves us with very deep, unanswered questions. It describes the particles and their properties, but it does not explain why they have those properties. Physicists found themselves in the position of needing to accept certain numbers as just given by nature. The exact mass of an electron, for example, is a number that must be measured in an experiment and then plugged into the equations by hand. The theory itself does not provide that number. We know what the properties are, but we do not know why they are what they are. It's like having a list of ingredients, but no recipe that explains them. String theory proposes a radical departure from this view. It suggests that this building block model is only an approximation, a surface-level description of a much deeper reality. It asks, what if the particles we've been studying are not the true fundamental objects at all? What if they are, instead, the results of something else happening at a smaller scale? The core proposal of string theory is that the universe is not made of many different types of particles. Instead, it suggests there is only one fundamental object. This object is not a zero-dimensional point, but a tiny one-dimensional loop of energy, which we call a string. This is a profound shift in perspective. According to this theory, All the different particles we observe are actually the same object, just in different states of motion. The strings are constantly vibrating, and the specific pattern of vibration is what matters. A string that vibrates in one specific, repeating pattern will appear to our experiments as an electron. It will have the exact mass, the exact negative charge, and all the other properties that we associate with an electron. If that very same string stops vibrating in that pattern and begins to vibrate in a different pattern, its properties will change. It will cease to be an electron and will, for all measurable purposes, become a different particle entirely, such as a photon, which is a particle of light. If the string vibrates in another distinct way, it appears as a quark, a building block of protons and neutrons. In this view, the universe is not a collection of different things, but rather a symphony of different notes. The properties we measure, like mass, are just reflections of the energy or frequency of the vibration. A slowly vibrating string appears as a low-mass particle, while a rapidly high-energy vibrating string appears as a high-mass particle. This idea is elegant, but its true power, and the reason it has fascinated physicists for decades, is that it offers a solution to the single greatest conflict in modern science. For the last century, our understanding of the universe has been split between two pillars. The first pillar is general relativity, Albert Einstein's theory of gravity. It describes the universe on the largest scales, explaining how planets, stars, and galaxies move by describing gravity as the curvature of space and time. It is a smooth, geometric theory that works perfectly for the large-scale cosmos. The second pillar is quantum mechanics. This is the set of rules that governs the universe at the smallest possible scales, the strange, probabilistic world of atoms, electrons, and subatomic particles. This theory is also perfectly accurate in its own domain. The problem is that these two theories are mathematically incompatible. They are written in different languages. General relativity is smooth and deterministic. Quantum mechanics is jumpy, probabilistic, and deals in discrete packets of energy called quanta. This isn't just an abstract disagreement. It is a real barrier to our understanding. To describe the most extreme environments in the universe, physicists need both theories. To understand what happens at the exact center of a black hole, where an immense amount of gravity is crushed into a tiny quantum-sized space, we need both. To describe the first fraction of a second of the Big Bang, where the entire universe was smaller than an atom but contained all of its mass and gravity, we need both. But when the equations of general relativity and quantum mechanics are combined, they fail. The math breaks, producing nonsensical answers, like infinity. This mathematical failure happens because the old theories assume particles like electrons are point-like, meaning they have zero dimensions. When you try to calculate the interaction of gravity and quantum rules at zero distance, the equations collapse. String theory resolves this conflict. A string, unlike a point, is not zero-dimensional. It has a tiny, but real, one-dimensional length. It is an extended object. When two strings interact, they don't meet at an infinitely small point. Their interaction is slightly smeared out across their tiny length. This small change is all it takes to fix the mathematics. The infinities that previously broke the equations simply disappear. The math becomes consistent. Within this new, consistent framework, gravity is no longer the odd one out. A specific vibrational pattern of the string emerged from the equations. This predicted particle had zero mass, and the exact properties required to be the graviton, the long-sought, hypothetical particle that carries the force of gravity. For the first time, string theory provided a way to describe gravity in the same quantum language as all the other forces of nature. However, this powerful solution comes at a very high conceptual price. The mathematics of string theory is only consistent if the universe does not just have the 4 dimensions we perceive, 3 of space, length, width, height, and 1 of time. The equations demand the existence of extra spatial dimensions. Depending on the specific version of the theory, it might require a total of 10 or even 11 dimensions, meaning 6 or 7 extra dimensions of space. This is a startling claim. If they are real, why can we not see them? The theory's answer is that these extra dimensions are compactified. That is, they are curled up on themselves at an impossibly small scale, far smaller than an atom. They are folded into the fabric of reality at every single point in space, but they are too small for us, or even light, to access. These hidden dimensions are not just a passive background, they are critical. The theory suggests that the shape and size of these tiny, curled up dimensions are what dictate the rules of vibration. They constrain the strings, determining which vibrational notes are allowed and which are not. This, in turn, is what would determine the properties of the particles we see. It could finally provide the recipe we were missing, explaining why the electron has its specific mass, because that is the vibrational frequency allowed by the geometry of the extra dimensions. This idea leads directly to another, even more speculative concept. If the laws of physics are determined by the shape of the hidden dimensions, what if those dimensions could be folded in more than one way? The theory suggests a vast landscape of possible geometries. Each stable possible folding would create a different universe with its own set of rules. Our universe, with its specific physical constants, would be just one of many possibilities, a bubble of reality with its own unique physics. It is essential to state clearly that all of this, the strings, the extra dimensions, the multiverse, remains a theoretical and mathematical framework. It is unproven. No experiment has yet provided direct evidence for strings. Its power, and the reason it remains so central to physics, is that it is the most complete and elegant mathematical structure ever proposed that allows for the unification of all known physics into a single, coherent picture. This core idea of vibration in string theory does not stop with the strings themselves. The theory proposes that this principle must also apply to the very fabric of space and time. In our established understanding, following Einstein's general relativity, we already know that space-time is not a fixed, rigid, or passive background. It is a dynamic entity. It can be stretched, warped, and curved by the presence of matter and energy, and this curvature is what we experience as the force of gravity. String theory takes this concept a significant step further. It suggests that space-time is not just flexible and malleable, but that it is also subject to vibrations, much like the strings that move within it. If the specific vibrations of the strings are what create the particles of matter, then the vibrations of space-time itself might be what create the fundamental structure and properties of the universe. This line of thought is directly connected to one of the most famous and most challenging aspects of the theory, the absolute requirement for extra dimensions. In our daily lives, we experience a world of 3 spatial dimensions: length, width, and depth. We can move forward or backward, left or right, up or down. We also move through one dimension of time. This four-dimensional reality is the limit of our perception. However, for the mathematics of string theory to function, for it to be internally consistent, and to successfully unite all the known forces of nature, this four-dimensional picture is insufficient. The equations do not work. They demand the existence of additional spatial dimensions that are hidden from our view. Depending on the specific version of the theory being used, the total number of dimensions is often 10, 9 of space, 1 of time, or even 11. This is, understandably, a very difficult concept to grasp. If these other dimensions are real, why can we not see them or move through them? The theory provides a specific answer. These extra dimensions are compactified. This means they are curled up or folded in on themselves at an impossibly small scale. They are believed to be smaller than the smallest distance we have ever been able to measure, far smaller than an atomic nucleus. They exist at every single point in our familiar space, but they are too tiny for us, or even for light, to access or perceive. These hidden dimensions are not just a strange mathematical quirk or a side effect. They are absolutely central to how the theory works. The specific geometry, the exact shape and size of these tiny, curled up dimensions is what would determine how the fundamental strings are allowed to vibrate. Imagine a string on a violin. The note it produces is determined by its length and tension. In the same way, the notes the fundamental strings can play are determined by the tiny, complex space they are vibrating within. The shape of these hidden dimensions would act as the set of rules for the music of the universe. They would constrain the strings, dictating which vibrations, and thus which particles, are possible and which are not. This mechanism, for the first time, offers a potential answer to why our universe has the properties it does. It could explain why an electron has its specific mass and its specific charge. In the old model, these are just numbers we measure and accept. In string theory, these properties would be a direct consequence of the allowed vibrations, which are themselves a consequence of the shape of the hidden dimensions. This idea also offers a potential solution to one of the greatest puzzles in all of physics, the weakness of gravity. We experience gravity as a powerful force, easily holding us to the surface of the Earth. But when compared to the other fundamental forces, it is astonishingly weak. The electromagnetic force holding a small household magnet to a refrigerator door is easily overpowering the combined gravitational pull of the entire planet Earth. String theory suggests this weakness might be an illusion, a matter of perspective. Some models of the theory propose that most forces, like electromagnetism, are confined to our familiar four dimensions. The strings that create those forces are stuck to our dimensional sheet. Gravity, however, is different. The particle that carries gravity, the graviton, is unique in that it is not stuck. It is free to travel and leak out into all the extra hidden dimensions. Because its influence is diluted by being spread so thin across this much larger, multidimensional space, it only appears weak to us who are trapped in our four-dimensional section of reality. This framework also leads naturally to another, even more speculative idea, the multiverse. The theory suggests there is not just one way for these extra dimensions to be curled up. The mathematics allows for a vast landscape of possibilities, perhaps an almost infinite number of different stable shapes and geometries that these dimensions could take. Each of these possible geometries would create a different set of rules for string vibration. This means each stable geometry would result in a different universe with its own unique set of physical laws. Our universe, with its specific constants and its particular collection of particles, would be just one bubble in this larger multiverse, defined by the particular way our extra dimensions happen to fold. Other universes could exist with radically different laws. Perhaps gravity is a strong force, or light travels at a different speed, or electrons do not exist at all. So, when we look at the world around us, we are not just seeing solid, static objects in a passive, three-dimensional space. If string theory is correct, we are seeing the results of complex vibrations. We are seeing particles and forces that are shaped by the geometry of dimensions we cannot observe. The universe we experience is just the visible surface of a much deeper, more complex, multi-dimensional reality. This is the grand suggestion of string theory, that the universe is not made of many different types of stuff. It is not a collection of separate, solid particles. It is a single, vast, interconnected system. At its most fundamental level, reality is a web of vibrating energy. The strings that make up matter and the space-time they exist in are all part of this unified process. This framework is powerful because it successfully brings together the two pillars of modern physics, quantum mechanics and general relativity. As we've discussed, these two theories have long been in conflict. Quantum mechanics works perfectly for the small-scale world of particles, while general relativity works perfectly for the large-scale world of gravity. But they fail when combined, especially when trying to describe the singularity at the center of a black hole or the first instant of the Big Bang. String theory, by replacing zero-dimensional point particles with one-dimensional strings, fundamentally resolves this conflict. The mathematical breakdowns, the infinities, in the old theories happened at zero distance. Because a string has a tiny length, it never interacts at a single zero distance point. Its interactions are smeared out just enough to prevent these mathematical failures. In this unified picture, all the fundamental forces are seen as different expressions of the same underlying object. The electromagnetic force, the nuclear forces, and the force of gravity are all, in this view, just different vibrational patterns, different notes played by the same fundamental strings. It is crucial, however, to be clear that string theory is not yet proven. Its mathematics is incredibly complex, and we currently have no way to test it directly. The energies required to see an individual string are far beyond any technology we can build. Its power, for now, is its mathematical consistency and its comprehensive explanation. It suggests that the reality we perceive is a dynamic, constantly shifting symphony of vibrations stretching across dimensions we cannot see. When physicists first began developing the mathematics of string theory, they found that the equations only worked. They only became consistent and free of contradictions if the universe contained 10 dimensions. This was 9 dimensions of space and 1 of time. This was already a radical proposal. But as the theory was refined and as different versions of it began to merge, a new picture emerged. When the influence of gravity was fully incorporated, many physicists concluded that 11 dimensions, 10 of space, and 1 of time were necessary to fully explain the interactions of all the forces in a single, unified framework. This requirement for a specific number of dimensions is not arbitrary. It is a result of the mathematics itself. It can be compared to assembling a complex puzzle. If you are missing a piece, or if you try to force a piece that doesn't belong, the puzzle simply does not fit together. The equations of string theory only fit together and produce sensible results when this specific number of dimensions is included. The immediate, obvious question is, if these dimensions are real, why do we not notice them? We move in 3 spatial directions, and no more. The answer within the theory is that these extra dimensions are hidden from our perception because they are incredibly small. They are compactified, meaning they are folded up or curled so tightly that they exist only at the tiniest possible scales, far beyond the reach of our senses or any current scientific instrument. We can think of them as tiny, intricate creases in a sheet of paper that are invisible until you get extremely close, or like extra pages of a book that are hidden within its spine. They are part of the structure, but not easily accessible or observable. And yet, even though we cannot see them, these extra dimensions are not just a passive background. They would be fundamentally important. As mentioned before, they could influence the universe we do see. For example, the relative strength of gravity could be explained by the structure of these extra dimensions. In some versions of the theory, gravity is not confined to the 3 familiar dimensions of space. It is the one force that can spread out, or leak, across all 11 dimensions. The other forces, like electromagnetism, might be stuck to our 3-dimensional sheet of the universe. If gravity's influence is diluted by being spread so thin across many more dimensions, it would naturally appear much weaker to us in the 3 dimensions we can observe, even if its fundamental strength is just as high as the other forces. This idea of hidden dimensions also opens up a fascinating, though highly speculative, possibility that there might be other universes, each with its own set of dimensions and its own physical laws. This is the multiverse scenario. If string theory allows for many different ways for these extra dimensions to be folded or arranged, then perhaps our universe is just one of many. Each different arrangement of dimensions could create a different set of rules. Some universes might have only a few large dimensions, while others might have many more. In each of these universes, the strings would vibrate differently, creating entirely different sets of particles and forces. This is a mind-boggling thought, but it arises as a natural consequence of the theory's mathematics. If string theory is correct, and there really are 11 dimensions hidden beneath the surface of reality, then the universe is far more complex than we have ever imagined. The reality we see, feel, and touch would be only the surface layer of a much deeper, more intricate structure. These extra dimensions would provide the stage on which the fundamental strings vibrate, and the shape of that stage would determine the music. They would be the hidden symphony of the universe, the silent orchestra that plays the song of existence. This framework could, for the first time, explain why our universe has the particular properties it does. Why are the forces of nature balanced at just the right strength? Why do atoms form in the specific way they do, allowing for chemistry and ultimately for life? Perhaps it is because the specific shape of our hidden dimensions only allows for the string vibrations that create our specific physics. For all its mathematical beauty, however, string theory remains a work in progress. The extra dimensions, while an essential part of the equations, are still beyond our experimental reach. We cannot observe them directly, and we do not have the technology to probe such small scales. This leads to the central problem facing the theory today. It is, as yet, unproven. It is an elegant, breathtakingly complex mathematical structure, but it remains unfinished. Its promise lies in its potential to unify all the forces of nature into a single, cohesive framework. For decades, physicists have searched for a theory of everything, a single set of equations that could explain gravity, electromagnetism, and the nuclear forces as different aspects of one underlying principle. String theory is the most promising candidate we have ever had, but its elegance is not proof. The problem lies in its scale. The strings themselves are thought to be so incredibly tiny that they are far beyond the reach of our most powerful instruments. They exist on a scale so minuscule, it is difficult to even imagine how we could detect them directly. This creates a central challenge. How do you prove a theory that deals with components that are, for all practical purposes, invisible? Scientists are not trying to see a string. Instead, they are looking for indirect ways to test the theory's predictions. One such test involves searching for the effects of these extra dimensions. If they exist, they might not be completely sealed off. Perhaps at very high energies like those created in our most powerful particle accelerators, such as the Large Hadron Collider, we might be able to kick a particle hard enough that it flies off into one of these extra dimensions, disappearing from our detectors in a very specific, measurable way. So far, no such event has been observed. Another way to test the theory is through the study of black holes. String theory makes specific predictions about the nature of black holes, suggesting their behavior might be different from what our current theories predict. Studying the fine details of black holes, perhaps through gravitational waves, could offer valuable clues. However, these are incredibly complex calculations, and the theoretical models are still being refined. And then there is the problem of the multiverse. If the theory's prediction of multiple universes is correct, how could we ever test it? If these other universes are, by definition, separate from our own, how could we gather evidence for them? This is a deep, philosophical problem at the border of science. This lack of experimental confirmation leaves us in a state of scientific limbo. We have a theory that is mathematically beautiful and offers solutions to our deepest problems, but we cannot say for certain if it is the correct description of reality. This does not mean the theory is useless. String theory has already led to profound insights and breakthroughs in pure mathematics. It has inspired new ways of thinking about space, time, and gravity, and provided new tools for understanding quantum mechanics. But as a physical theory, it remains an unfinished piece of music. We can appreciate its beauty and its complex structure, but we are still waiting for the final notes that would provide experimental confirmation. The unfinished nature of string theory is a reminder of the complexity of the universe and the limits of our current understanding. As we journey deeper into this theoretical framework, we encounter even stranger concepts. We've discussed the basic idea of one-dimensional vibrating strings, but the theory has evolved. Scientists began to consider what happens when these strings form closed loops. A loop is a string that doesn't have ends, but is instead connected to itself, like a tiny, vibrating rubber band. These loops can move freely through space-time, twisting and turning. Their properties are very important, as they offer new ways to think about particles. For example, the graviton, the particle of gravity, is predicted to be a closed-loop string. But loops are just the beginning. As string theory evolved into a more comprehensive framework, sometimes called M-theory, which incorporates the 11-dimensional idea, scientists began to consider more complex objects called brains. Brain is short for membrane. Just as a string is a one-dimensional object, a brain is a higher dimensional object. A two-dimensional brain would be like an infinite sheet or membrane. A three-dimensional brain would be a volume, and the theory allows for brains of even higher dimensions. In this expanded view, strings are not the only fundamental objects. These multidimensional brains are also fundamental. This leads to a startling new picture of the cosmos. In some of these models, our entire universe, everything we can see, all the stars and galaxies might exist on one of these brains. We could be living on a giant, three-dimensional sheet that is floating within a larger, higher dimensional space, the bulk. In this scenario, the strings that make up matter and light, like electrons and photons, might be stuck to our brain, unable to leave it. This would explain why we only perceive three dimensions. But gravity, as a vibration of space-time itself, would not be stuck. It would be free to move through the bulk as well as on our brain. This provides another, more concrete explanation for why gravity seems so much weaker than the other forces. Its influence is being shared with the vast, higher dimensional space that we cannot access. This concept of higher dimensional objects introduces a more complex set of components into the theory. These are known as brains, a term shortened from membranes. A string is a one-dimensional object. A brain, however, can have any number of dimensions. A two-dimensional brain, or two-brain, would be like an infinite flat sheet. A three-brain would be an infinite three-dimensional volume. String theory evolved to suggest that these brains are just as fundamental to the structure of reality as the strings themselves. This leads to one of the most speculative and revolutionary ideas in modern physics, known as the brain world hypothesis. This hypothesis suggests that our entire observable universe, every star, every galaxy, every atom, and every one of us might exist on a single, vast, three-dimensional brain. In this model, our 3D brain is not the entirety of existence. It is, instead, floating within a much larger, higher dimensional space, a space that might have 10 or 11 dimensions in total. This higher dimensional space is referred to as the bulk. This idea would explain, in a very direct way, why we only perceive three dimensions of space. We are, in this view, physically stuck to the brain. The theory provides a mechanism for this. The particles that make up matter, like electrons and quarks, and the particles that carry most of the forces, like photons, are theorized to be open strings. This means they have two ends. These ends, according to the model, are stuck to our three brain. They can move freely along the brain in our three dimensions, but they cannot detach and fly off into the bulk. This would confine us and most of the physics we know to this three-dimensional sheet of reality. However, this model makes a crucial exception for gravity, the particle that is predicted to carry the force of gravity. The graviton is not an open string. The theory predicts it is a closed-loop string. It has no ends, and therefore it has nothing to stick to our brain. This means that while we are trapped on the brain, gravity is not. The graviton is free to travel, not only along our brain, but also off of it into the full, higher dimensional space of the bulk. This provides a new and powerful explanation for one of the oldest mysteries in physics. Why is gravity so incredibly weak? Compared to the other forces, it is astronomically weaker. The electromagnetic force holding a small magnet to a metal surface can easily defeat the entire gravitational pull of the planet Earth. The brain-world hypothesis suggests that gravity isn't fundamentally weak. It is just as strong as the other forces, but its influence is diluted because it can spread out into all the extra hidden dimensions of the bulk. Only a tiny fraction of its true strength is felt by us on our brain. The other forces seem strong only because their energy is completely confined to our dimensions. This idea, while speculative, is not just a story. It has testable consequences. If this model is correct, it might be possible, in very high-energy particle collisions, to create a graviton that flies off into the bulk. This would appear to our detectors as energy that simply vanishes, a specific signature that physicists are actively searching for. This framework also offers a natural home for the concept of the multiverse. If our universe is one three-brain floating in the bulk, what else is out there? The theory allows for the existence of other brains, perhaps parallel to our own, also floating in the bulk. These could be other universes. They might be separated from us by a tiny distance, perhaps less than a millimeter, but in a higher dimension we cannot access. These parallel universes would be invisible to us, and their matter and light would be stuck to them, just as ours is stuck to us. The only force that could pass between these brains would be gravity. These other brain worlds could have very different properties. The way their extra dimensions are folded, or the way their strings vibrate, could create a completely different set of physical laws. They might be universes with different particles, different forces, or no stars at all. It is essential to understand that this entire structure, the strings, the brains, the bulk, is not a classical mechanical system. It is governed by the rules of the hidden realm, the world of quantum mechanics. To understand string theory, we must first accept the bizarre nature of the very small. In the quantum world, reality is fundamentally different from our everyday experience. Objects do not have definite, solid properties. A particle, like an electron, is not a tiny billiard ball. It does not have a precise location or a precise speed until the moment it is measured. Before that, it exists only as a wave of possibility, a mathematical description called a wave function that represents all its potential states at once. It is in a constant quantum dance of uncertainty. String theory is, at its very core, a quantum theory. This means the fundamental strings themselves obey these rules. A string is not just vibrating in one pattern. It exists in a superposition of many different vibrations at once, until an interaction forces it to choose one, which we then observe as a specific particle. The space-time fabric itself is believed to be a quantum foam at the smallest scales, a chaotic, vibrating sea of possibilities. Perhaps the most baffling feature of this quantum world is entanglement. Two particles can be created in a linked state. Their properties, while individually uncertain, are connected. If they fly apart, even to opposite ends of the galaxy, they remain part of a single system. The instant an observer measures a property of one particle, the state of the other particle is instantly known, determined. This appears to be instantaneous communication, something Albert Einstein called spooky action at a distance. It does not violate the speed of light because no information is being sent. Rather, it shows that our idea of separate objects is an illusion. At the deepest level, the universe is not a collection of individual parts. It is a single, deeply interconnected whole. This quantum strangeness is at the heart of the central problem that string theory was developed to solve: the conflict between our two greatest theories of the universe. For the last century, physics has rested on two pillars. The first is Einstein's general theory of relativity. This is the theory of the large. It describes gravity not as a force, but as the curvature of space and time. Massive objects warp space-time, and other objects follow those curves. It perfectly describes planets, stars, and the expansion of the universe. The second pillar is quantum mechanics. This is the theory of the small. It perfectly describes the probabilistic world of particles, atoms, and the other three forces of nature. These two theories work perfectly in their own domains, but they are completely mathematically incompatible. They are written in different languages. General relativity is smooth, continuous, and deterministic. Quantum mechanics is jumpy, probabilistic, and uncertain. For most of physics, this is not a problem, but there are two places in the universe where both theories must apply: at the center of a black hole and at the first instant of the Big Bang. In these singularities, an immense amount of mass and gravity, requiring general relativity, is crushed into a single quantum-sized point, requiring quantum mechanics. When physicists try to apply both sets of equations to these scenarios, the math fails. It returns answers of infinity, which is the mathematical way of saying the theories are broken and do not describe reality. This is where string theory provides its solution. It is not an attempt to add quantum rules to gravity. It is a quantum theory from the very beginning from which gravity emerges. The conflict in the old theories happened because they were built on point particles, objects with zero dimensions. The math broke down at zero distance. String theory replaces these points with one-dimensional strings. A string has a tiny, but not zero, length. It smears out the interaction. There is no longer an infinitely small point or a zero distance. This smearing is just enough to fix the mathematics. The infinities that broke physics disappear. And, most beautifully, the theory predicts gravity. As physicists explored the mathematics of string vibrations, they found that one specific vibrational pattern, a closed-loop string with a specific energy and spin, had the exact properties of the graviton, the hypothetical quantum particle of gravity. In string theory, gravity is not the odd one out. It is just another note in the quantum symphony. It is the vibration of a string, just as an electron and a photon are. For the first time, this provides a single, unified quantum framework that describes all forces and all matter as originating from the same fundamental object. What makes gravity so unique, however, is that unlike the other fundamental forces, it is incredibly weak. Electromagnetism, for instance, is vastly stronger than gravity. The strong and weak nuclear forces, which operate inside the atom, are even more powerful. This raises a critical question. Why is gravity so much weaker than all the other forces? In string theory, the proposed answer lies in the hidden dimensions that the theory requires. As we've discussed, string theory suggests our universe has more than the familiar 3 dimensions of space and 1 of time. It may have as many as 11 dimensions in total, with the extra ones curled up so tightly that we cannot directly perceive them. The idea is that gravity, unlike the other forces, is not confined to our three familiar spatial dimensions. Instead, its influence is allowed to spread out, or leak, across all of the extra, hidden dimensions. In this view, gravity appears weak to us because its total strength is diluted. The other forces, in contrast, are stuck to our three-dimensional brain or sheet, and so their full strength is concentrated here. This could explain why gravity seems so feeble in comparison. It is simply not as focused in our part of reality. But even though gravity might seem weaker in our everyday experience, it has a hidden power. In the quantum world and in extreme environments, gravity is still a dominant force. Near black holes, or during the first moments of the universe, gravity is the most important force at play. String theory suggests that the force of gravity could become incredibly strong at the tiniest scales, and that the very fabric of space-time itself is influenced by the vibrations of the fundamental strings. This means gravity is not just an external force acting at a distance, but a deep, intrinsic part of the universe, woven into the very structure of reality. The nature of gravity in string theory may also hold the key to some of the biggest unsolved mysteries in physics. These include the true nature of black holes, the origins of the universe, and, most importantly, the relationship between quantum mechanics and general relativity. String theory suggests that understanding gravity's behavior on the smallest scales, its quantum nature, could help us understand how space and time themselves behave at that fundamental level. This could finally lead to a working theory of quantum gravity, one that unites the strange, probabilistic world of quantum mechanics with the smooth, curved space-time of general relativity. But there is a catch. Just as with string theory as a whole, this beautiful picture of gravity is, as of now, unproven. We cannot directly observe the graviton, the particle that would carry the gravitational force. We do not have the technology to measure the effects of the extra dimensions that might explain gravity's weakness. We do not yet have the tools to probe the quantum nature of gravity at all. We do not know exactly how to test string theory's predictions in a way that would give us conclusive evidence. And yet, the theory offers a tantalizing possibility. It suggests that gravity, which we once thought of as a simple force of attraction, is actually a complex, multi-dimensional vibration, a resonant pulse that echoes throughout all dimensions of the universe, shaping the fabric of reality itself. This perspective gives us a new way of thinking about the cosmos. Instead of seeing gravity as a force that simply pulls things together, we can begin to see it as an integral part of a cosmic symphony. It is a vibration that carries information, influences the structure of space-time, and connects everything in the universe. Gravity's secret voice, in this view, is not a quiet, passive force. It is an active player in the dance of the cosmos. There are places in the universe where this force becomes so extreme that even light itself cannot escape. These are places so dense and so warped by gravity that they bend the very fabric of space and time. These are the black holes, the cosmic enigmas that have fascinated scientists for generations. Black holes are often thought of as the ultimate voids, the endpoint where space and time break down. They are described as having a singularity at their center, a point of infinite density where our current understanding of physics simply falls apart. But what if black holes, instead of being the end of everything, were actually part of the universe's ongoing song? String theory presents this fascinating possibility. According to this theory, black holes might not just be gravitational traps. They may also be places where the very vibrations of the strings, the building blocks of the universe, are stretched and distorted in extreme ways. Some physicists suggest that black holes might be a kind of cosmic instrument resonating with the vibrations of the universe. To understand this, we must first recall what a black hole is. It forms when a very massive star runs out of fuel and collapses under its own immense gravity. As the star's core contracts, it becomes so dense that its gravitational pull becomes overwhelmingly strong. It becomes so strong that it creates a boundary called an event horizon. Anything that crosses this boundary, including light, cannot escape. It is the point of no return. Inside this boundary, all paths lead toward the singularity, where space-time itself is thought to be infinitely curved. But string theory suggests black holes may not be this simple. Rather than being a single point of infinite density, a black hole, in string theory, might be a complex, multidimensional object, perhaps a brain, or a very dense tangle of strings. In this view, black holes are not just points, but are higher dimensional objects that vibrate and interact with the rest of the universe. Just as vibrating strings give rise to particles, the vibrations of a black hole itself could give rise to new forms of energy and information. This leads to one of the most profound ideas in modern physics. For decades, scientists have grappled with the black hole information paradox. Physics demands that information about a particle or system cannot be permanently destroyed. Yet, under the old rules, anything that falls into a black hole seems to be lost forever, its information erased. String theory offers a solution. It suggests that the information is not lost. Instead, it could be encoded in the vibrations of the strings and brains that make up the black hole itself. The information is preserved in the unique way the black hole resonates. If this idea is proven, it would mean that black holes are not just cosmic prisons, but intricate, vibrating structures that store information about the universe. They would not be places where the laws of physics break down, but places where they operate in a new, complex way. But how could we ever test this idea? We cannot directly measure the vibrations of a black hole. However, we now have a new tool. In 2015, scientists made history by detecting gravitational waves ripples in the fabric of space-time itself, caused by the collision of two black holes. This discovery confirmed a key prediction of general relativity and opened a new window onto the universe. If black holes are indeed vibrating objects, as string theory suggests, their collisions and movements should create specific patterns in these gravitational waves. By studying the details of these waves, scientists might one day be able to hear the song of the black hole and learn about its structure. This idea is highly speculative, but it suggests that the black holes populating our universe are not just silent, empty voids. They are active parts of the ongoing cosmic symphony, playing their own unique notes in the grand composition of reality. There is another strange kind of connection in the universe, one that defies our common sense of distance and time. It is called quantum entanglement, and it might be one of the most mysterious phenomena in all of physics. At its heart, it is the idea that two particles can become linked in such a way that what happens to one instantly affects the other, no matter how far apart they are. Einstein famously called this spooky action at a distance. Decades of experiments have shown that it is very real. But string theory places this strange idea into an even grander context. If everything in the universe is made of tiny vibrating strings, then entanglement isn't just an odd quantum trick. It might be a fundamental feature of the cosmic symphony. It could be the mechanism by which the universe maintains its hidden harmony. Imagine two strings vibrating in perfect unison. In quantum mechanics, when particles interact, they can become entangled. Their properties become forever linked. If you measure a property, like the spin of one particle, you instantly know the spin of the other, even if it is on the other side of the galaxy. This is not because information is traveling between them faster than light. That is impossible. Instead, it's because, in a very real sense, they were never truly separate objects to begin with. In the quantum world, distance does not work the same way it does for us. Entangled particles are part of the same underlying system, connected by something deeper than the space between them. If string theory is correct, that something deeper might be the strings themselves. What we perceive as two separate particles might just be two parts of the same underlying vibration, or two notes in the same hidden chord, forever tied together. Entanglement also leads to startling implications about the nature of reality. For one, it challenges our idea of locality, the common sense notion that an object can only be affected by its immediate surroundings. In the world of quantum entanglement, what happens at one location can instantly influence what happens at another, without any known signal or force traveling between them. It is as if the universe itself does not care about the boundaries we perceive as space. If everything is truly built from strings that exist in higher dimensions, then this non-locality might not be strange at all. It might simply be the natural consequence of a universe that is far more connected than it appears on the surface. This deep interconnectedness might even extend beyond individual particles. Some researchers have speculated that quantum entanglement could be the very glue that holds space-time together. It might be the deep stitching that binds reality into a single, coherent whole. There is a bold idea in theoretical physics that the fabric of space-time itself might emerge from quantum entanglement. In other words, the geometry of the universe, its shape, its structure, and its dimensions could be the large-scale result of countless entangled strings vibrating in unison. In this view, entanglement is not just a weird quantum curiosity. It would be the fundamental reason that a stable reality exists at all. It would be the hidden harmony beneath the surface of the cosmos, the reason the notes of the universe play together instead of collapsing into chaos. Even black holes, those mysterious engines of gravity, may be tied to entanglement. An idea known as the ER equals EPR conjecture suggests that two entangled particles might be connected by a microscopic wormhole, a tiny tunnel through space-time. If this is correct, then the universe could be filled with these hidden connections, microscopic shortcuts linking distant regions of space, all born from the entanglement of quantum particles. In a way, it would mean that every pair of entangled particles forms a tiny, invisible bridge in the unseen architecture of the cosmos, a subtle reminder that nothing in this universe is truly isolated. This, once again, ties us back to string theory's central theme. If every particle, every force, and every point in space-time is just the vibration of a string, then entanglement might be what happens when those vibrations overlap and lock into a shared harmony. The universe, in this picture, is not just made of individual, separate notes. It is made of chords, and those chords do not care about distance. They resonate across the entire score of existence. Time is something we experience so constantly that we rarely question it. It ticks along predictably, measured by clocks and marked by the cycles of day and night. But when you step into the world of string theory, time becomes far less straightforward. It stops behaving like the steady, constant river we imagine and starts to look like another part of the music itself. It becomes a rhythm that emerges from the vibration of the universe's fundamental strings. In our everyday lives, time feels linear and absolute. One moment follows the next, and the past flows irreversibly into the future. But physics has been challenging this intuition for over a century. Einstein's theory of relativity showed us that time is not universal. It is flexible. It stretches and compresses depending on how fast you move or how close you are to a massive object. Two people moving at different speeds will literally experience different amounts of time passing. String theory takes this idea even further. In a universe built from vibrating strings, time is not a separate entity. The vibrations of the strings do not just create particles and forces. They are also thought to give rise to the very structure of space and time itself. In this view, time is not an independent backdrop, like a stage on which the universe performs. It is one of the notes in the grand symphony. This leads to a profound question. If the strings of the universe were to stop vibrating, if the music fell silent, would time itself stop too? Some physicists have wondered if time, as we experience it, is not fundamental at all. It could be an emergent property, something that arises from deeper, more basic processes. In other words, time might not be a basic ingredient of reality. It might be something that appears when the vibrations of the universe interact in a complex way, just as a melody emerges from the playing of individual notes. This perspective would also help explain why time behaves so strangely at the quantum level. In the world of particles and strings, time does not seem to flow in a neat, orderly line. Quantum mechanics describes a realm where events do not always have a clear before and after, and where the usual order of time seems to blur. If time is not fundamental, but is instead a product of string resonance, then this strange quantum timelessness begins to make sense. It is not that time is broken. It is just the raw, unformed state of reality before our familiar experience of time emerges from it. This also ties into one of the biggest puzzles in physics. Why does time seem to have a direction? In our experience, time always flows forward. We grow older, never younger. A glass shatters, but never spontaneously reassembles. This arrow of time has long been linked to entropy, the tendency of systems to move from order to disorder. But if strings are the foundation of everything, perhaps this arrow is not just about disorder. Perhaps it is built into the way the vibrations of the universe unfold, like a complex symphony that can only be played from beginning to end, never in reverse. String theory even opens the door to the idea that time could behave differently in other regions of the cosmos, or even in other universes within a multiverse. If there are extra, hidden dimensions, and if strings vibrate differently within those dimensions, then perhaps time flows at a different rate there, or loops back on itself, or does not exist at all in the way we know it. If time is part of the music of strings, then we are not just passengers moving through time. We are woven into it. Our lives are, in this sense, strands of vibration that resonate within this cosmic rhythm. Every moment and every thought is part and distinguishable from the same deep structure that gives rise to matter, energy, and space. And yet, we live inside the familiar experience of the clock. Perhaps this is the most remarkable thing. The universe has taken this incredibly abstract, high-dimensional vibration and produced the simple, steady tick-tock that we can feel and measure. When we look at a clock, we are witnessing a surface-level expression of something unimaginably deep. If string theory is right, then every particle, every force, and even space and time itself come from the vibration of tiny, unseen strings. This raises a simple, yet unsettling question. What would happen if the strings stopped vibrating? What if the music of the universe fell silent? To answer this, we must understand what vibration means in this context. In string theory, vibration is not just motion, it is existence. An electron is an electron because its string vibrates in a very specific pattern. A photon is a photon because its string oscillates in a different pattern. If those vibrations ceased, the particles examples of this would no longer be what they are. They would cease to exist. This is difficult to grasp because we are used to thinking of the world in terms of solid objects. We picture particles as tiny, enduring marbles. But in string theory, the strings are not things in that sense. They are processes. Their vibration is what defines them. If you take away the vibration, the string itself is no longer a particle. It is like plucking a guitar string and then instantly muting it. The note stops. But in the case of the universe, that silence would not just be the absence of sound, it would be the absence of everything. However, there is a strange part. According to quantum mechanics, the strings of the universe can never be truly silent, even in what we call empty space. The quantum vacuum is not empty. It is buzzing with energy. Particles flicker into and out of existence. Strings are constantly humming at their lowest possible energy state, a fundamental level of vibration that cannot be reduced any further. This is sometimes called the zero-point energy of the universe. It means that even the quietest parts of reality are never truly still. The music never completely stops. Imagining total silence, however, is a useful thought experiment. It shows us how deeply vibration is tied to reality. Without it, there would be no particles, no forces, and no space or time. Silence, in this deepest sense, would mean non-existence. This makes the constant, underlying hum of existence all the more extraordinary. The universe does not just exist, it persists, sustained by a ceaseless, fundamental motion. Some versions of string theory suggest there might be multiple ground states for reality, different ways the strings could settle into a stable, minimal vibration. Each one of these would create a different version of the universe. In one of these hypothetical universes, the strings might be in a state that is, compared to ours, silent. In such a reality, what we consider matter, space, and time might not exist in any familiar form. Some physicists have even speculated that at the very beginning of our universe, before the Big Bang, there might have been a state of perfect symmetry, a kind of silent state where nothing was yet distinct. And then something broke that silence. The strings began to vibrate in the complex patterns we know, and in that first instant, reality as we know it came into being. In this view, the universe is the sound of that primordial silence breaking. But silence is not gone entirely. Black holes, for example, come eerily close to it. When matter falls into a black hole, it is drawn toward the singularity. If string theory is correct, the strings that make up that matter might be stretched and distorted in ways that almost extinguish their normal vibrations, creating a kind of frozen, timeless region. What happens there is still one of the biggest mysteries in physics. And then there is the far, far future. Physicists predict that one day, trillions of years from now, the stars will burn out and matter itself may decay. The universe might approach a final heat death, an endless, cold, dark expanse. In this state, the strings would vibrate only at their lowest possible zero-point energy. It would not be true, absolute silence, but it would be the quietest the universe could ever become. A universe where that complex music has slowed to a single, endless, almost inaudible hum. And yet, even in that far-off, theoretical quiet, there is a form of persistence. If the strings, according to the laws of quantum mechanics, can never truly stop vibrating, but must always retain their base-level zero-point energy, then the universe never truly dies in the sense of becoming nothing. It would simply keep humming, invisibly, endlessly. That fundamental, required vibration might be what keeps reality from ever slipping back into the total silence of non-existence. If the universe is a song created by these vibrations, then the next question posed by the theory is a profound one. Perhaps it is not the only song. Maybe what we call the universe, all the stars and galaxies we can ever see, is just a single melody in an endless concert of realities. Each of these realities would be playing its own tune, each built from its own unique set of vibrating strings. This is the idea of the multiverse. Within string theory, this is not just a philosophical speculation. It could be a direct, natural, and unavoidable consequence of the mathematics. The equations of string theory do not, at this point, provide one single, unique solution that describes our world. When physicists tried to solve the equations to find the answer, they discovered the opposite. They found that there was not just one solution, but a truly vast number of possible solutions. This collection of possibilities is often called the landscape of string theory. Each of these solutions corresponds to a different, stable way for the universe to be. Specifically, each solution represents a different way for the hidden, extra dimensions to be folded up or compactified. The theory suggests that the shape of these tiny, curled-up dimensions is what dictates the laws of physics. Their geometry determines how the strings are allowed to vibrate, which in turn sets the properties of all particles and all forces. One shape for the hidden dimensions might create a universe where gravity is strong and electrons are heavy. A different shape might create a universe with no gravity at all, or with 4 types of light. The mathematics suggests that there could be as many as 10 to the power of 500 possible stable universes. This number is so large that it becomes almost meaningless to the human mind. It is a 1 followed by 500 zeros. It is a number far, far greater than the total number of atoms in our entire observable universe. In this multiverse picture, every single one of these mathematical solutions is physically real. Each one is its own concert hall, with its own unique instruments and its own separate melody. Some of these universes might be familiar, differing only slightly from ours, but the vast majority would be radically different, so alien that they would be unrecognizable realities, where matter as we know it is unstable, where stars cannot form, where chemistry is impossible. This idea raises a staggering question. Why are we in this universe and not one of the countless others? Why are the strings here vibrating in just the right, complex way to give us stars, planets, and the precise conditions necessary for life? If there are 10 to the 500 universes, perhaps the answer is not one of design, but of selection. We find ourselves in this particular universe for the same reason we find ourselves living on a planet and not in the empty void of space. We are here because this is one of the rare universes where the vibrations and the physical laws happen to produce conditions that allow observers like us to exist. This concept is sometimes called the anthropic principle. It suggests that our universe is not special. It is simply one room in a near infinite concert hall, and we happen to be in one of the few rooms where the music is stable and complex enough for listeners to evolve. In all the other universes, where the strings hum in different, simpler, or more chaotic patterns, there is no one there to observe them. But there is another, deeper possibility. If all these universes exist, are they truly separate, or are they connected in some hidden way? Some versions of the theory suggest that these universes might not be completely isolated. Perhaps, under extreme conditions, it would be possible for one universe to tunnel into another, or for universes to collide. Some physicists have even speculated that certain large-scale anomalies in our own sky, perhaps a strange cold spot in the cosmic microwave background, the afterglow of the Big Bang might be a bruise, a faint residual echo from a collision with another universe in the distant past. Even if we never detect those echoes, the multiverse concept fundamentally changes the way we see ourselves. It means our universe is not the entire story. It is just one performance, one arrangement of the cosmic strings, among a countless, incomprehensible number of others. It is at this moment, when a discussion is about 11 hidden dimensions, vibrating strings smaller than anything we can ever hope to observe, and an infinite sea of parallel universes, that one must wonder, is this still science, or have we stepped into the realm of philosophy? This tension has always been part of physics. Science, by its definition, must be built on what we can see, measure, and test. It builds from experiment and observation. But the deeper we have probed, the stranger the universe has become. Atoms were once considered unthinkably small, until we discovered the particles within them. Space and time once seemed absolute, until relativity showed us that they bend and stretch. Now, string theory asks us to go even further, to accept that what we see is just a faint surface, a mere shadow of a much larger, more intricate reality. But if we cannot prove it, if we cannot test it, is it truly physics? This is a fair and serious question, one that scientists themselves argue about. Critics of string theory point directly to its lack of direct experimental evidence. They argue that a theory that cannot be tested, or more importantly, a theory that cannot be proven false, is not science. It is just an elegant mathematical story. And if the multiverse is real, the theory might become untestable. If every possible outcome exists in some universe, then the theory cannot make a specific prediction for our own, and it risks explaining nothing. And yet, there is another side to this. Historically, many of the greatest breakthroughs in science began as ideas that were completely untestable at the time they were proposed. When ancient Greek philosophers first suggested the idea of atoms, it was pure philosophy, with no way to prove it for over 2,000 years. When Einstein proposed general relativity, there was no immediate way to prove that massive objects truly bend space-time. It took years for the technology and experiments to catch up. Perhaps string theory is not the end of science. Perhaps it is simply in a new phase, one that stretches the boundary between physics and philosophy until the line between them begins to blur. The universe, after all, does not care about our human labels. It simply is. There is also a deeper point. String theory, whether or not it is ultimately proven correct, forces us to confront questions that physics has often avoided. Traditional science has focused on the how. How does gravity work? How do particles interact? But string theory, by presenting a landscape of 10, 500 possible universes, forces us to ask why. Why this universe? Why these vibrations and not others? Why is there something rather than nothing? These are questions that feel philosophical because they dig into the very roots of existence. But it is not all speculation. Even if we cannot detect strings, the framework of string theory has given physicists powerful new mathematical tools for understanding other, more testable areas of science. It has led to profound new insights into the mathematics of black holes. It has inspired new research in quantum field theory and our understanding of the early universe. In this sense, it is already more than just philosophy. It is a powerful engine for exploration. Still, there is no denying the mystery. Perhaps that is why string theory holds such a grip on the imagination. It tells us that the universe is music, that everything is connected, and that beneath the surface of our ordinary world lies a hidden structure of extraordinary beauty. So, is it physics or is it philosophy? Maybe it is both. Maybe it is what happens when physics becomes so ambitious that it begins to ask the same questions philosophers have asked for millennia, only now it is armed with equations. At its best, science has never just been about prediction. It is about wonder. It is about looking at the universe and refusing to accept that what we see is all there is. If you have ever listened to a perfectly played piece of music, you know there is something almost mathematical about it. Each note falls into place with precision. String theory suggests this is no accident. Mathematics and music share a deep connection because the universe itself seems to be built from that connection. For centuries, mathematics has been the language of physics. From the elliptical paths of planets to the behavior of subatomic particles, every law of nature we have discovered can be expressed in numbers and equations. But string theory takes this relationship a step further. It does not just use math to describe reality. It suggests that mathematics is the foundation of reality. In string theory, the universe is not made of little solid objects that just happen to follow mathematical rules. It is made of vibrations, and those vibrations are the mathematical patterns. Each string has its own frequency, its own mode of oscillation, and those frequencies determine everything: the particles that exist, the forces that act between them, and the very shape of space and time. This is where the beauty of the theory lies. If you strip away all the complexity, you are left with an elegant idea. Reality is mathematics in motion. Every particle is an equation turned into a vibration. Every force is a mathematical relationship. We, along with the stars and galaxies, are part of that same grand calculation. This leads to one of the deepest questions in science. Is mathematics something humans invented, or is it something we discovered? Is it merely a useful language we created to describe the world, or is it the fundamental blueprint of reality itself? It is astonishing how well this language maps onto the structure of the universe. String theory leans heavily toward the idea that math was discovered. It suggests that the universe is not just a physical thing that happens to obey mathematical laws. It proposes, instead, that the laws themselves are the universe. In this view, matter, energy, space, and time are nothing more than the physical manifestations of deep, underlying mathematical truths. This is not just a philosophical preference. It is a requirement of the equations. The extra dimensions that string theory predicts are a perfect example. They were not added to the theory because they seemed interesting. They were added because the mathematics required them. Without them, the equations break down and become inconsistent. When physicists follow this mathematical trail, it does not just lead to one unique answer for our universe. It leads to an entire landscape of possible universes, perhaps 10 to the 500th power different solutions. Each one of these is a different, mathematically valid solution to the same underlying equations. It is as if mathematics is not just a language for describing the cosmos, but is the score the cosmos is playing. And just as in music, small changes in that score can create entirely different melodies. If a string vibrates in a slightly different mathematical pattern, it creates a different particle. If the mathematical structure of a hidden dimension is changed, the result could be a universe where gravity is stronger, or where atoms cannot form, or where time itself behaves in ways we can barely imagine. This trust in the math comes from a long history of it predicting reality. Einstein's equations predicted black holes decades before any astronomer had observed one. Quantum theory predicted the existence of specific particles long before experiments had the power to confirm them. In the same way, the mathematics of string theory has led physicists to new insights and ideas about gravity, quantum entanglement, and the deep structure of space-time itself. The hope is that these predictions, too, will one day be confirmed. This perspective suggests the universe itself is a kind of mathematical object. It might exist not because it was created in a physical sense, but because it had to exist, simply because the mathematics allowed for it. This is where the theory's elegance becomes almost unsettling. If everything is a vibration, and every vibration follows a precise mathematical rule, then perhaps the universe has no choice but to be what it is. Maybe the reason we are here at all is because this is one of the ways the math could play out. Of course, this raises as many questions as it answers. Why this mathematics and not some other? Why do the strings vibrate in exactly these ways? Even if we do not know the answers, the idea suggests that beneath all the complexity, all the chaos of reality, there lies a kind of pure, crystalline order, a mathematical framework so deep and intricate that it gives rise to everything. Science, however, must always be a conversation between theory and experiment. Theories propose explanations, and experiments must test those ideas against physical reality. Sometimes experiments confirm what was suspected, and other times they surprise us, forcing a complete rethinking. String theory sits at the current edge of this process. It is an elegant framework, but it is one that is still waiting for experiments to catch up and reveal whether its bold predictions reflect the universe we actually live in. For decades, the theory has been primarily mathematical. This is because the components it describes are at scales that are almost impossible to imagine. The strings themselves are thought to be incredibly small, far beyond the reach of any current technology. The energy scales required to probe them directly are unimaginably high, far greater than what even our most powerful particle accelerators can achieve. The central challenge, then, has been this: how do you test a theory about things you can never hope to see directly? Scientists have devised several clever, indirect ways to look for signs of string theory in our universe. One approach is to search for evidence of the extra dimensions it predicts. Although these dimensions are hidden and compactified, or curled up so tightly that we cannot observe them, they might still have a subtle influence on the behavior of particles and forces in our world. For example, the presence of extra dimensions could alter the properties of gravity at very small scales. Researchers have conducted extremely precise experiments to test whether gravity behaves differently than expected at tiny distances. So far, no deviations have been found. The search continues, with more sensitive experiments being planned. Another avenue involves the study of cosmic phenomena. The early universe, just moments after the Big Bang, was an extreme environment. The energies and densities were unimaginably high, perhaps high enough to reveal the effects of vibrating strings. Cosmologists, therefore, look to the cosmic microwave background, the faint, leftover radiation, or afterglow, of the Big Bang for subtle patterns. These tiny fluctuations in this ancient radiation could, in theory, carry information about the universe's earliest moments, including the possible behavior of strings. Future missions with more precise measurements could shed light on this. A new window into the cosmos was opened with the first direct detection of gravitational waves in 2015. These are ripples in the very fabric of space-time, caused by cataclysmic events like merging black holes. These waves travel across the universe and might carry clues about the structure of space-time at the smallest possible scales. If string theory is correct, the vibrations of strings could leave subtle signatures in the gravitational waves we observe. Scientists are developing ways to analyze this new gravitational wave data for such effects, hoping to catch whispers of the string's cosmic dance. Particle physics experiments also play a crucial role. Machines like the Large Hadron Collider, or LHC, are our most powerful tools for testing these ideas. They work by smashing particles together at incredible energies. The goal is to recreate the conditions of the very early universe, and in doing so, to hopefully create new particles or observe new phenomena that are not predicted by our current established theories. Some versions of string theory predict the existence of such exotic particles. If the theory is correct and the energy of the collision is high enough, we might see these new particles appear in the detectors. So far, the LHC has not found direct evidence for string theory, but this is still useful data. These results have pushed the boundaries, allowing physicists to rule out some specific versions or models of the theory. This guides the theorists toward more refined models and helps narrow down the search. The gap between a complex theory and a definitive experiment can be daunting, but it is not unprecedented in science. The history of physics is full of important ideas that took decades or even centuries to be tested. When the concept of atoms was first proposed by ancient philosophers, it was purely a philosophical idea, completely without experimental proof. It took the development of entirely new technologies and a new understanding of chemistry and physics to finally confirm their existence. In the same way, the predictions of Einstein's general relativity were just mathematics on a page until an experiment could be devised. It was only years after he proposed the theory that an eclipse of the sun allowed scientists to observe the bending of starlight, confirming his prediction. String theory, in this sense, is at a similar crossroads. It is a theory rich in mathematical beauty and potential, but it is still awaiting its own definitive experimental validation. The hope is that future advances, perhaps in particle physics, in cosmology, in quantum computing, or in some entirely new field, will provide the tools needed to finally test its predictions more directly. There is also a sense in which the theory has already proven useful. The complex mathematics developed specifically for string theory has found surprising applications in other unrelated areas of physics. Insights from string theory have helped scientists better understand difficult problems in condensed matter physics, such as superconductivity. It has also provided new ways to think about quantum information and entanglement. This shows that even if the strings themselves remain hidden, the theoretical framework itself is a powerful tool. So, while string theory's ultimate test may lie in the future, the dialogue between theory and experiment continues. Each new discovery, whether at the LHC or from a distant telescope, refines our understanding, shaping the theory and guiding the search. If string theory is ever proven to be the correct description of reality, the implications are not just for physics. The implications would extend to our understanding of ourselves. It would mean that we are not just living in a universe made of strings. It would mean that we are made of strings. Every atom in our bodies, every particle in our blood, and every electrical flicker of thought in our minds would arise from the fundamental vibrations of these invisible threads. Life, in this view, is not something separate from the cosmos. It is one of the complex patterns that the universe can produce. This is a humbling thought. For most of human history, we have seen ourselves as separate from the great machinery of the cosmos. We have viewed ourselves as observers looking out at a distant and separate universe. But string theory invites us to see it differently. It suggests there is no out there and in here. There is only one vast, interconnected network of vibration, and we are an inseparable part of it. Think about it this way. Your body is a collection of atoms. Each of those atoms is built from fundamental particles, such as electrons and quarks. In string theory, each of those particles is simply a particular pattern of vibration, a specific frequency of a fundamental string. Therefore, in a very real sense, a human being is an incredibly complex collection of these vibrations, a living, stable pattern in the structure of the cosmos. The rhythm of a heartbeat, the firing of neurons, the flow of blood, all of it is a high-level process built upon a world that is already vibrating at the deepest level imaginable. If everything is vibration, then what we call biology might be nothing more and nothing less than a special and highly organized arrangement of those vibrations. It is one of the many ways that the universe organizes its own fundamental patterns. This view changes how we might think about our place in the cosmos. If we are part of this process, then we exist because the strings are vibrating in just the right way. We exist because the hidden dimensions are folded in just the right shape, and because the laws of physics that emerge from those vibrations align to create a world where matter can form, where stars can burn, and where complex life can emerge. In another universe, one of the many others allowed by the theory's mathematics, the vibrations might be different. In that universe, there might be no life at all. Or perhaps there might be forms of organized structure so strange we would not recognize them. They might not be carbon-based organisms, but stable patterns of vibration that exist in ways we cannot currently imagine. If string theory is true, then life, like everything else, is written into the fundamental rules of the vibrations. This also raises a profound question about consciousness. If the universe is a symphony of strings, what role do we play? Are we just listeners, or are we part of the process itself? Some physicists and philosophers have wondered if consciousness could be linked to this deep structure. Perhaps what we experience as thought is another form of vibration, an emergent, complex resonance that arises from the brain, which itself is born from the same fundamental patterns that give rise to all other matter and energy. This is speculative, but it suggests our awareness, our ability to wonder about the universe, is not an accident. It is part of the same physical structure. This leads to a final possibility. What if life is not just a byproduct of the universe, but something the universe does naturally? If vibrating strings give rise to particles, and particles give rise to chemistry, and chemistry gives rise to biology, then life may be woven into the structure of reality from the beginning. The same laws that govern black holes and galaxies also govern the beating of your heart. The same vibrations that create stars also create you. When you think about it that way, it becomes hard to feel entirely separate from the cosmos. If the universe is built on these vibrations, then everything, every star, every tree, every fleeting moment of life is part of the same performance. We are not spectators watching from a distance. We are notes in the structure, resonating in a universe that has been vibrating since the beginning of time. We are woven into it, inseparable from it, part of a process that was playing long before we were here and will keep playing long after. Consciousness is the quiet mystery at the center of our existence. We live every moment of our lives inside it, yet we still do not fully understand what it is or where it comes from. Science has made progress in explaining how the brain works, how neurons fire, how signals move through the brain, and how chemistry and biology shape our thoughts. But none of this explains why we have a subjective, internal experience. It does not explain why the universe seems to look out at itself through our eyes. When this question is placed inside the framework of string theory, the mystery deepens. If the entire universe is built from fundamental vibrating strings, and if everything we see and touch is born from these vibrations, then what is consciousness? Is it something separate from this physical structure, or is it a product of it? One way to think about it is this: if every particle in our bodies and every atom in our brains is made of strings vibrating at specific frequencies, then consciousness cannot be separate. It must emerge from these vibrations. In this view, awareness is not a thing, but an emergent property. It might be an incredibly complex pattern formed by countless strings vibrating in a highly organized way, not just in our brains, but throughout the matter that makes up our physical selves. This idea is not entirely without parallels. Even in neuroscience, researchers are exploring the idea that consciousness is deeply connected to patterns of oscillation. Brain waves, those rhythmic pulses of electrical activity, are measurable vibrations. When we think, dream, or focus, the rhythm and frequency of these waves change. While this is happening at a biological level, string theory suggests that there is an even deeper, more fundamental layer of vibration beneath it all, stretching down to the basic fabric of the universe. What if consciousness is simply what happens when the universe's fundamental vibrations become organized in a way that allows them to process information about themselves? There is a certain logic to that thought. If we are made of the same vibrating energy as everything else, the physical processes of the cosmos do not just surround us, They happen through us. Perhaps consciousness is the internal experience of that complex, self-referencing pattern. This might also explain why consciousness is so difficult to define or locate. If it is an emergent property of vibration, a pattern arising from the deepest levels of reality, it would not be located in a single part of the brain or in a single atom. It would be a distributed process. If this is true, it could also mean that consciousness is not unique to us. If vibration is fundamental, and if awareness can emerge from complex arrangements of those vibrations, then perhaps the universe is filled with other forms of awareness that we cannot recognize. They might be alien patterns of consciousness built on different kinds of matter, different physical laws, or even existing in different dimensions. And what about the universe itself? If every string in the cosmos is connected, and if those vibrations connect across all dimensions, could the cosmos as a whole have some form of awareness? It would not be a mind like ours, but perhaps a vaster, stranger field of resonance, with every conscious being existing as a small flicker within it. These are not questions we can answer yet. They may not even be questions we are ready to ask properly, but they follow naturally from the logic of a universe built on vibration. If the cosmos is a physical process, then we are not separate from that process. We are the part of it that has become complex enough to be aware of it. Whether consciousness is just a biological phenomenon or something woven into the very structure of the universe, string theory invites us to see it differently. It is not an accident and not an isolated spark, but another part of the physical process. If string theory is true, then everything is a pattern of vibration, not as a metaphor, but in a literal sense. Every particle, every force, and every thread of space-time is a note, a specific, soundless frequency in the deepest structure of reality. If that is what the universe is, then what does that make us? We are both the process and the result. At the smallest scale, we are vibrations stacked upon vibrations. Quarks, which are themselves specific vibrational patterns, hum together to form protons and neutrons. Electrons orbit atomic nuclei, and their specific energy levels are determined by quantum rules. Those quantum rules are, in this framework, expressions of this fundamental vibration. Atoms, governed by these rules, join together to form stable molecules. These molecules then bind into vast, complex chains, which in turn build the machinery of cells. Those cells organize and differentiate, building tissues, organs, and eventually a complete, functioning organism. Layer upon layer, pattern upon pattern, what emerges is not just a random collection of matter, but a highly organized, self-sustaining system. In this sense, a biological entity is a living arrangement. It is a complex cord struck from the same fundamental strings that weave the fabric of galaxies and stars. The frequencies that shape inert matter are the exact same frequencies that shape biology. In this view, there is no fundamental boundary, no magical line between a physical existence and the underlying processes of the universe. They are a continuum of the same process, vibrating in time with a rhythm that is older than the Earth itself. Yet, there is a clear, functional difference between simple and complex structures. A rock, a crystal, or a body of water might resonate with the same fundamental strings. Its atoms are all vibrations, but it does not process information about its own existence or its environment beyond simple physical cause and effect. Certain complex systems, however, develop this ability. Structures like a brain, which are networks of billions of interconnected cells, do not just exist, they model the world around them. This is the phenomenon we call consciousness. If this theoretical framework is correct, then consciousness itself must be fundamentally tied to these vibrations. It cannot be something that floats above the physical structure, separate from the physics. It must be an emergent property of the system. Awareness, in this view, could be a specific type of resonance. It would be an incredibly complex, organized, and self-referencing pattern formed by countless strings vibrating in harmony, primarily within the brain, but existing throughout the entire biological system. This idea is not entirely without parallels in conventional science. Even in neuroscience, researchers explore the concept that consciousness is deeply connected to measurable patterns of oscillation. The brain's activity is not random. It is organized into rhythmic electrical pulses known as brainwaves. These are measurable, biological scale vibrations. When a brain is focused, dreaming, or in deep sleep, the rhythm, frequency, and coherence of these waves change dramatically. While this is observed at the biological level, string theory suggests that there is an even deeper, more fundamental layer of vibration beneath it all. This underlying hum stretches down to the basic fabric of the universe itself. Consciousness, then, could be the mechanism that arises when the universe's vibrations become organized in a way that allows them to process information about their own state. This perspective might explain why consciousness is so difficult to define. If it is an emergent property of vibration, a pattern rather than a thing, it would not be located in a single part of the brain or in any single atom. It would be a distributed, holistic property of the entire functioning system. If vibration is fundamental, and if awareness can emerge from complex arrangements of vibration, it also suggests that the universe could be filled with other forms of awareness. These would be forms that are completely unrecognizable to us, alien patterns of consciousness, perhaps not even biological, built on different kinds of matter, operating under different physical laws, or even existing primarily in other hidden dimensions. This entire theoretical framework, however, is not just about constant, chaotic motion. A stable reality, one that can form patterns like atoms and galaxies, requires structure. That structure is defined by stillness, just as much as it is defined by sound. In music, it is the silence between the notes that gives the melody its shape and rhythm. Without the pauses, all the notes would blur into a single, meaningless noise. The universe must operate in the same way. String theory, therefore, cannot just describe a universe of random motion. It must also provide the stillness inside that motion. The tiny strings vibrate, but their movement happens against the backdrop of a stable structure, the defined shape of the extra dimensions, and the fundamental laws of quantum mechanics. The silence between the notes of reality is not empty. It is the structure that gives the patterns their meaning. It is what allows a particle to be distinct from another. We often focus on the motion, the energy, the particles, the theories, and the discoveries. But the stable, silent structure is just as much a part of the system. It is in the pause between one quantum state and the next. It is in the vast, stable geometry of space that separates galaxies. If the universe is truly built from these vibrations, its existence is held, supported, and made possible by its own quiet, underlying structure. That stillness, as much as the vibration itself, is where the universe lives. It is all part of one vast and unbroken system. The process, the song, goes on, always.